Thank you, Chairman, for your kind introduction. I hope that you can all see me and hear me well. I'm really sorry that I cannot be with you in Thailand. I mean, I'm pretty sure that the weather is much better than in London right now. But yeah, well, what can you do? I hope that you're having a nice time there, and thank you for allowing me the possibility to participate in the conference through this online talk. So my name is Emilio Martinez-Paneda. I'm a UK senior lecturer, so equivalent to associate professor in the US, and UKRI Future Leaders Fellow at Imperial College London. Today, I want to present some work that I've done, some papers that I've done before joining Imperial College, actually, when I was a research fellow working with Norman Fleck at the University of Cambridge. And we published a few papers just before the pandemic, so I haven't had the chance to talk about them in conferences and so on. So let me go ahead and try to explain what we try to do. But I should also say that this is work that is building up on previous work that I've done with other collaborators, such as Christian Nilsson at DTU, Covadonga Betegon at the University of Oviedo, and many others. And our goal has always been to try to understand what is the role of plastic string gradients of geometrically necessary dislocations in the fracture process of metallic materials. And our motivation comes from the fact that we often see that under special circumstances, experiments show cleavage fracture in the presence of significant plasticity. This, of course, doesn't happen all the time. Most metals fail in a ductile manner, but often we see that maybe due to low temperatures, due to the fact that the steel has been embrittled, due to the presence of an aggressive species like hydrogen, or maybe because the steel is next to ceramics, so you have a biomaterial. In many of the circumstances, we can see that we get very clean fracture surfaces indicative of atomic decohesion, while at the same time we can measure significant plastic flow. And this has always been quite puzzling for us, because we know that atomic decohesion requires stresses, attractive stresses on the order of the atomic or the theoretical lattice strength, which is 10 times the yield stress. Even if we think of a grain boundary, we know that we need stress on the order of 9 times the yield stress to effectively decohere a grain boundary. So this is puzzling to us because in the context of conventional continuum theories, there's no way that we can achieve those high level of stress that are needed to reach these cleavage fractures that we see in those experiments. And I mean, we know this going back almost 40 years now, right? Thinking of the work of Bob McMeekin. Bob McMeekin, during his PhD thesis, was the first to simulate using finite element analysis what would be the stress fields that are predicted ahead of a crack, taking into account large strains. And as you can see, this is taken from one of his earlier papers. The maximum stress level that you get ahead of your crack is 3 times the yield stress. So we're very far away from those 10 times yield stress requirements that are needed to achieve the cleavage strength. And this, of course, can change a little bit, whether you have a bit of hardening in your material. It may be that your maximum stress is 4 times the yield stress, but still you're very far away. So this is basically our conundrum. Experiments are telling us that we are hitting this level, this brittle fracture threshold, but conventional continuum theories, when we do analysis, finite element analysis of stresses ahead of a crack, tells us that we're still very far away. So we are having stresses on the order of 4 times the yield stress. So what is happening here? What are we missing? How can we jump from here to here, basically? And our main hypothesis is that what we're missing in this picture is the role of plastic strain gradients and geometrically necessary dislocations. And the main motivation here comes from the experiments. And there's a very wide range of experiments, particularly at the micro scale, that show that geometrically necessary dislocations or plastic strain gradients can increase the flow strength in metals. But I'm going to illustrate this concept with this set of experiments by Fleck and co-workers on thin copper wires, because they're really clean and beautiful, in my opinion. So as you can see here, they tested very thin copper wires of different diameters under both uniaxial tension and also in torsion. And as you can see in uniaxial tension, those strain curves that they obtained were roughly insensitive to the diameter of the wire. You can see that more or less all the curves fall on top of each other independently of the diameter of the wire. However, in torsion, when we go to these normalized stress strain curves, you can see there is a very significant size effect, with thinner wires being much stronger than thicker wires. You can see that the flow stress for thinner wires could be 3-4 times the one of thicker wires. And this is quite remarkable because these are, again, normalized curves, kind of stress, equivalent stress strain curves. So there's quite a significant size effect that you cannot capture with conventional theory, right? So in a way, that is the critical observation, that whenever you have homogeneous strain distribution, like you have in uniaxial tension, so no gradients of plastic strain, then there's no stress elevation. However, whenever you introduce gradients of plastic strain, geometrically necessary dislocations, then you get a very significant stress elevation associated with this plastic strain gradients. And this is important because if I try to simulate these results using conventional continuum theories, for example, using von Mises plasticity, then I wouldn't be able to capture this phenomena. I will basically predict that all the curves fall on top of each other, as we see in the uniaxial tension case, but I wouldn't be able to capture this elevation of a strength. So that is the bad news. Conventional continuum theories are not able to capture this role of GNDs and plastic strain gradients because they have no length scale in their constitutive equations. However, the good news is that a number of very clever mechanicians have devoted their efforts to extend plasticity theory to small scales. And this goes back all the way to the pioneering work of Elias Aifantis, and then has been followed by many others, as you can see here in the slide. And the key point is that you build these strain gradient plasticity theories by typically defining your flow stress as a function of not only the plastic strains, but also the plastic strain gradients, or defining the plastic work, again, not only a function of the plastic strains, but also of the plastic strain gradients. And of course, the moment you bring a gradient of deformation here into the picture, then you need a length scale due to dimensional consistency. And this length scale is a material parameter that somehow characterizes the ability of a material to harden in the presence of these geometrically necessary dislocations of these plastic strain gradients. Because as you can see in the experiments, what these GNDs are doing is basically acting as obstacles to the movement of statistically stored dislocations, and therefore elevating the stresses. And the good news is that using these gradient plasticity theories and fitting this length scale, which you can think of something like the strain hardening exponent, right? A material parameter that characterizes the hardening abilities of our material. So when you fit that length scale that typically gives you a value between 1 and 10 microns, you see that you're able to get a very good agreement with experiments. And these are finite element predictions of those experiments on thin copper wires, and these are from Lorenzo Bardella and Andrea Panteghini, and you can see that they get a very good agreement. So we are able to use these strain gradient plasticity models to predict what is the role of GNDs and plastic strain gradients. So this is what we want to do in fracture. And I should emphasize one thing here. When I'm talking about fracture and gradient effects and size effects, I'm not anymore talking about small samples, small, very thin wires. I'm talking about large samples which have a small plastic zone adjacent to the crack tip. And this is similar to what you see in indentation, right? So you have an indenter here, you may be indenting a very large sample, but you get size effects associated to the fact that you have a small plastic zone near your indenter tip. So the size effects are related to the size of the plastic zone, not necessarily the size of the sample. Which this means, or the implication that results from this, is that no matter the size of your sample, whenever you have a crack, you're typically going to have a plastic zone that is physically small, and that therefore will contain strong spatial gradients of deformation and a very significant GND dislocation density. And as I said before, those GNDs are going to act as obstacles to the movement of the statistically stored dislocations and are going to elevate the stresses near a crack, in that region near the crack where plastic strain gradients are significant. And in fact, nowadays we can measure GND densities ahead of crack tips and inclusions, and what we see from experiments is that GND densities are very large and dominate material behavior near inclusions and cracks. And in fact, if you take one of those strain gradient plasticity models and decide to simulate the stresses ahead of your crack, you see what you see in the slide. So this is the tensile stress ahead of the crack. So the crack will be here, and this is the distance ahead of the crack in micrometers. And this is a simulation run with a strain gradient plasticity model. And in the dashed line, you see there's the result predicted with conventional plasticity. And effectively, what you see is that far away from the crack tip, both conventional plasticity and strain gradient plasticity agree. However, as you approach the crack tip, then GNDs start to dominate over statistically stored dislocations. You have a strong influence of this plastic strain gradient. You have those dislocation hardening mechanisms kicking in. And as a result of that, you get a very significant stress elevation. So the implications from a fracture mechanics point of view is that if you're dealing with a fracture phenomenon where the critical distance for fracture, the fracture process zone is very large, like for example, ductile fracture, then, well, you don't really care that much about these G&D effects, about these plastic strain gradients, because essentially you are hundreds of microns away from your crack tip. However, very often we have situations, and this is relevant to the experiment that we were discussing before, where you had a critical distance very close to the crack tip, within the order of 1 or a few microns. And there you can see that the stresses can be very different depending on which assumption you take. So if you're neglecting the role of G&Ds and plastic strain gradients, you're really significantly underestimating your stresses. So we tried to use this hypothesis. We said, okay, maybe this elevation in stress that results from G&Ds, from plastic strain gradients, is what is driving those brittle fracture processes. And we look into this by doing a cohesive zone analysis. So we tried to simulate a crack propagation. This is inspired on a classic paper by Terberger and Hutchinson in JMPS 1992, where they use cohesive zone elements and conventional von Mises plasticity to predict crack growth resistant curves, R curves, to predict the crack growth resistance associated with plasticity. And the idea is quite simple. So you basically place these cohesive elements along the crack propagation region, and these cohesive elements basically glue the two crack surfaces. And the behavior of this glue of these cohesive elements is governed by a traction separation law, like you see here, where the critical parameters are basically the area under the traction separation law, the fracture energy, the critical cohesive strength, so this sigma hat here, and then the shape of the traction separation law, which will give you this critical separation. And here we choose to follow Terberger and Hutchinson and use a trapezoidal traction separation law, which gives us this expression for the fracture energy as a function of the critical separation. And then, as in their paper, we can define a critical or reference stress intensity factor at which cracking will initiate, so whenever that corresponds to this fracture energy. And then you can also define a characteristic length of the fracture region, this R0 characteristic length of the fracture process zone, that is depending on the fracture energy, the yield stress, Young's modulus, and so on. And if you do a dimensional analysis, what you see is that the R curves, the crack growth resistant curves that you will predict, are essentially a function of these non-dimensional sets. And the only difference between their study and ours is that because we're using gradient plasticity, we have this additional non-dimensional set. So the ratio between the length scale that tells us how easy it is for the material to harden due to the presence of G&Ds, and this R0 is what is going to change the picture, what is going to govern material behavior. So before we look into crack propagation, we again look at the stationary crack tip fields, and you can see that this ratio between the length scale and in this case the plastic zone is what governs the material behavior. And as you would expect, the higher this value, the higher the value of this ratio, the more easy it is for a given load for the material to harden, to exhibit an elevation in stresses associated with these G&Ds. So this is all in agreement with expectations. And then we model this crack propagation curve, so this R curve. So this is the stress intensity factor, so a measure of the crack tip stresses of the applied load versus the crack extension, normalized by this R0. And you can see that depending on the value of the length scale, so you go from this very significant plastic dissipation that you get in the case of conventional plasticity, and this agrees with those results by Terberger and Hutchinson. But then as we increase this ratio of L divided by R0, then we see that we're having a very significant degradation of the stresses, of the fracture resistance, basically. You have much higher stresses, and therefore you lower your fracture resistance. And it's a key point to emphasize that what matters is the ratio between the two, because the length scale is a fixed parameter, it's a material property. We measure that doing indentation, we measure that doing microbending, we measure that doing microtorsion, like I showed you before, but that is a fixed material parameter. But these R0 depends on the applied load and on the fracture energy. So whenever you have maybe a ductile fracture process, then R0 is going to be quite large because the fracture energy will be on the order of thousands of kilojoules per square meter, and therefore this value is going to be small, and you're probably in a region where it doesn't matter. But whenever you have a brittle fracture process, this fracture energy is going to be small, maybe on the order of a few joules per square meter, and therefore this value is going to be small and this value is going to be large. So this is suggesting that we're going in the right direction. It seems that our results should not be independent on this ratio. We know that depending on the fracture process, you can have a plastic zone that is larger or smaller, and that's going to make a difference on your gradient effects. So what we do next is to compute the steady state toughness curve. So you see that these crack-growth curves, they all plateau at some point. So we're going to run them until we get to this plateau level, and this we're going to call the steady state fracture toughness. And we're going to compute that for different levels of the cohesive strength, because this cohesive strength you can relate to that atomistic decohesion strength that I discussed before, right? Now we're taking 4 times the yield stress, otherwise we wouldn't see anything with conventional plasticity, but we're going to change that number and see if we can get close to the cleavage strength. And this is what you see here. So first, I'm plotting the result for conventional plasticity. This agrees with this result by Teberger and Hutchinson. You can see that our steady state fracture toughness is very far away, basically asymptotically increases as you approach 4 times the yield stress, because these are the maximum stresses that you get with conventional plasticity. So there's no chance that you will be able to predict fracture using conventional plasticity models if you have a cleavage strength, if you have a grain boundary strength that is 10 times the yield stress. However, as we introduce gradient effects into our model, you can see that eventually, depending on the magnitude, on the ratio between this, on the value of this ratio, the length scale divided by R0, we're able to predict fracture even for values of our interface that are on the order of 10 times the yield stress, or even for the theoretical lattice strength. So that's quite interesting because, as I said before, this provides a mechanistic rationale to understand why we're seeing cleavage fracture in the presence of plasticity. And this is what is happening essentially, right? So you can have a lot of plastic work coming out for those dislocation densities, for the evolution of those dislocations, but you can still get very high stresses if your fracture region is small compared to the ability of the material to harden due to the presence of GNDs. And again, I emphasize that the length scale is a material parameter, but R0 is dependent on the fracture energy. So again, is dependent on the fracture micromechanisms that are taking place. And what is interesting is that, in fact, if you look at discrete dislocation dynamics, and this is taken from Bill Curtin's group, you can see that this is actually what they predict. So these are discrete dislocation dynamic simulations, and you can see that somehow they will also be able to capture eventually fracture near this region of 9-10 times the yield stress. So it seems to agree pretty well with some of the predictions of strain gradient plasticity. And this framework allows us to rationalize many of the experiments that I showed you before. Let me discuss some of them. So one of them is cleavage fracture in biomaterials. So the experiments by Korn et al. These are some classic seminal experiments where they measure, they had a crack between sapphire and niobium, and they measure very significant plastic work in niobium, but at the same time, when they look at the fracture surface, they saw a very clean fracture surface with a crack propagating in a brittle fashion between the sapphire and the niobium, so within the biomaterial. And what we see when we use one of these strain gradient plasticity models, in this case is Gortin's distortion gradient plasticity model, what we see is that when you account for the role of GNDs and plastic strain gradients, you see that your stresses are high enough so that you can predict this, you can attain this cleavage fracture strength that we discussed before. So in this set of experiments, for the loading conditions that they consider, we're able to get at the critical load stresses that are high enough over a sufficiently long distance such that a crack can grow. Another interesting case is low temperature cleavage. And what we did here is to use a Weibull model, a 3-parameter Weibull model, and calibrate those materials with a classic European project, it was not a European steel project where they had measures of probability of failure, where you can calibrate the probability of failure for different temperatures. And essentially, I mean, at the end of the day, a Weibull model is a fitting exercise. So we basically were able to see that we get very different values of M and the threshold and all the parameters involved in the Weibull model. But this doesn't really tell us much, right? Because in a way, we are calibrating the data. It just tells us that there's a big difference with conventional plasticity. However, what made a difference was the fact that we calculated this probability of failure maps, and we saw that if you had conventional plasticity, then your probability of failure, your hazard maps, were distributed over tens of millimeters, while if you have gradient plasticity, then your hazard maps, your probability of failures were restricted to tens of microns. And we know from the experiments that the critical distance in these materials is typically of tens of microns. So it seems that we're going in the right direction. And another area where this is very important is hydrogen-embrittled. we know that the presence of hydrogen, or when we expose metals to hydrogen-containing environments, we have an uptake of hydrogen, and this reduces by orders of magnitude the fracture resistance, the ductility, and the fatigue crack growth resistance of metals. So it's very important here, and it's important for a number of reasons. The first one is that the amount of hydrogen that you have in your material depends on your hydrostatic stress. You can see it here. Hydrogen accumulates in areas of high hydrostatic stress. This is the simplest equation one can use to simulate hydrogen transport within a metal. And this is the steady state equation, which, as you can see here, shows that there's a very significant dependence on the hydrostatic stress. You know, there's an exponential term here. So if you really want to know what your concentration of hydrogen is, and you really want to know that precisely to be able to predict these hydrogen-assisted failures, you need to know what is your hydrostatic stress. So as you can imagine, G&Ds are going to play a big role there. And there's another reason for this. And the other reason is that the critical distance for hydrogen embrittlement is 1 micron ahead of the crack tip or less, or around that number, basically. And you can get that from experiments, because in the hydrogen embrittlement, you basically see this 3-stage regime. Whenever you're plotting, you can see here crack velocity versus stress intensity factor. So you have a cracking threshold, you have a stage 1 where the crack speed grows significantly with the loading rate, but then you have this stage 2 where no matter how much you increase your stress intensity factor, your crack speed remains the same. And the reason why this happens is that because you have, this is a diffusion-dominated regime, basically. Your crack can only grow whenever the hydrogen has had enough time to reach the critical distance ahead of your crack. So the crack is effectively jumping whenever the hydrogen has reached the critical distance. So since we know from the experiments what is the crack speed, so for example, for this nickel superalloy, we know that is probably 0.04 microns per second. And then we know what is analytical solution for the diffusion of hydrogen atoms. That depends on the diffusion coefficient and the time. We effectively have 2 equations that we can solve for very easily. That gives us what is this critical distance, what is this jump of the crack, how long do we need to wait for the hydrogen to reach this critical distance, and what is this critical distance that we need to wait for the hydrogen to reach. And this is, for this specific case, knowing the diffusion coefficient of the material and knowing what is the crack speed, we can solve the system and get a critical distance of 1 micron. So at 1 micron, as we saw before, gradients play a big role, and we therefore need to account for G&Ds if we want to tackle this hydrogen embrittlement problem. And you can see here that if you plot the hydrogen concentration ahead of a crack, of course, as you would expect from the previous results, you see that in conventional plasticity, you're under-predicting very significantly what is the hydrogen concentration ahead of your crack tip compared to gradient plasticity. And it's very difficult to measure hydrogen content so close to your crack tip, but there are some experimental data out there, and we can see that they seem to predict what we predict with gradient plasticity. You can see here that the hydrogen concentration increases rather significantly as you approach the crack tip, where your conventional plasticity predictions are lying all the way here. And we use this rationale to try to understand the embrittlement process. And because in the embrittlement process, you basically have metals that fail in a ductile manner that suddenly fail in a brittle fashion due to the exposure to hydrogen. And you can see here, again, those steady state toughness versus cohesive strength calculations. This is, again, for a strain gradient plasticity model and using cohesive elements. And again, you can see that in an inert environment, these metals fail in a very ductile fashion. So with R naught being on the order of thousands of kilojoules per square meter, which means that this value is typically around 0.01. So as you can see here, in the absence of hydrogen, there's no way that we can cross this line. So failure will take place in a ductile manner. However, the moment we bring hydrogen into the picture, what we know from atomistic calculations and from experiments is that hydrogen is going to reduce this fracture energy. So this fracture energy is going to be reduced due to the presence of hydrogen atoms. The surface energy, the fracture energy, can be reduced by up to 40%, 50%, depending on the material, due to the presence of hydrogen atoms. So when we take that into account, this is going to change R naught, and therefore this ratio. So for a given strain gradient plasticity length scale, we see that suddenly all these curves shift. And now, due to the presence of hydrogen, we're going to be able to predict brittle failure at, even if we consider cohesive strengths on the order of the theoretical lattice strength or the grain boundary strength. So that takes me to the concluding remarks, hopefully leaving a bit of time for questions. So I just want to emphasize 3 takeaway points. The first one is that we believe that we have a hypothesis to understand why brittle fracture is often observed in the presence of significant plastic flow. And this is that we have very high crack tip stresses that are a result of the strain gradient hardening that arises due to the presence of GNDs and plastic strain gradients. And this is something that we can capture using strain gradient plasticity models. So we can use this class of constitutive models that are strain gradient plasticity models to capture that role of GND in plastic strain gradients. We calibrate them with experiments, and then we use them to predict what's going to happen ahead of a crack. And we have shown that by taking this into consideration, we can explain experiments showing the brittle failure of hydrogen-embrittled materials. We can explain low temperature cleavage, and we can explain also the fracture of B-material interfaces, among other phenomena. Thank you very much for your kind attention. And of course, many thanks to our sponsors. Thank you so much.